Now, let's talk about the hydrolysis of salts. Okay, now, earlier I kind of went on about thinking of the salts as the product of an acid-base reaction. Okay, so we had all those 4 reactions, and for each of them we always got a salt at the end of the day. Right? Now, hydrolysis basically is a fancy way of saying reacts with water. Okay, reacts with water. Now, here, what's going to happen is sometimes when a salt is formed, that salt is going to go and react again with water, and when it does that, it sometimes forms hydronium or hydroxide ions, which is then going to change the pH of the solution. Okay, so let's ask ourselves, well, why is a strong acid weak? Why is a strong acid strong? Okay, so HCl, for example, reacts with H2O, and that gives us Cl negative and hydronium ions. Okay, now basically, because this ionizes completely, the reaction goes one way. And one way of thinking about it is to say that actually this chloride is just really bad at reacting again in order to form the HCl. Because if it was really good at reacting again to form the HCl, well then HCl wouldn't be a strong acid, because as soon as it ionized, well, some of those ions would react again in order to form the HCl, and that's the idea there, right? So it gives us a principle, right? And the principle is the following. The ion from a strong substance, right, is inert. Okay, now inert is a fancy chemistry physics way of just saying it doesn't react again, right? And as we said, for strong acids or strong bases, well, if the ions that they formed did easily react again, then the reverse reaction would readily take place, and they probably wouldn't be strong. They wouldn't be able to ionize or dissociate completely. Whereas if we have something that is weak, so let's say we've got ammonia, which we know reacts with water, and we tend to use these double arrows for the weak acids and bases, the reversible reaction, right? Then we get the ammonium plus the hydroxide ions, right? So if you go look at the Kb value for this, you'll basically see that essentially at equilibrium, we've got lots of this and only a little bit of this. Okay, so what's happening here? Well, this poor ammonia, as soon as it manages to react with water to form the ammonium says, hold on, I'm really good at reacting in order to form you again. And then that reverse reaction readily takes place, and that's why the poor ammonia ends up as a weak base, because as soon as it does manage to ionize, well, then the reverse reaction takes place very easily, and so the ammonia is then formed again. And so we get an equilibrium where we actually still have lots of these reactants and not too many of these products. Okay, so what's the principle? Well, the principle is that the ion from the weak actually does react again. Okay, so those are our two principles, right? And we're going to see how we can use these principles in order to then go and figure out what's going to happen with our strong or weak acids and bases. Okay, so I am erasing it like this so that we can keep the principles on the board. So while I'm erasing, you look at those principles and you memorize them. You take them seriously. Okay, cool. Right, so let's see what happens if we have a strong acid and a strong base. Okay, so strong acid and a strong base. Okay, so a strong acid and a strong base might be something like hydrochloric acid and sodium hydroxide. And when these react, we're going to get sodium chloride and water. Okay, so the question is, sodium chloride, does it react again? Well, the sodium is going to be from strong, right? because it comes from sodium hydroxide, and the chloride is going to be from strong as well, right? Because it comes from the hydrochloric acid. And so since they're both from strong, we're going to have that neither of these are actually going to react. Okay, so neither of those are going to react again with water, and so this is what we call a neutral salt. Okay, so a neutral salt, you put it in water, it dissociates, but it doesn't change the pH of the water because it doesn't react again in order to form hydronium or hydroxide ions. Okay, so what is the importance of this? Well, basically, when you perform a titration, right, we need to stop the titration at the equivalence point, right? So the equivalence point is when all of the acid and all of the base has neutralized each other, right? Now, if all of this is gone, right, and we've just formed this, well then the sodium chloride is neutral, and so there's nothing in the solution that is going to change the pH, so we expect a neutral pH. So if we have a strong acid and a strong base, we need an indicator that's going to change color in a neutral range, because we said the endpoint is when the color changes, and we need the endpoint to coincide, i.e. happen at the same time as the equivalence point. So for this, we tend to use bromothymol blue, because the bromothymol blue actually changes color roundabout at a neutral pH. Okay, so let's see what happens if we have a strong acid and a weak base. Okay, strong acid, weak base. Okay, so let's say that we've got HCl plus the ammonia that we saw earlier, and that is going to form ammonium chloride. Something like this. Okay, so if we ask ourselves what's going to happen here, well, the chloride is not going to react again, right? Because it comes from the strong hydrogen chloride, hydrochloric acid, and we know that the ion from the strong does not react. It's inert. So the ammonium is from weak. So from weak means it does react again with water. So let's see what that's going to look like, right? So if we have the ammonium reacting with water, well, we know that the ammonium wants to give away that proton that it gained in order to form the ammonia again, right? But when it does that, it's now actually giving it away, which means the water receives a proton to form hydronium. But hydronium ions is what makes something acidic. Right? So this salt, ammonium chloride, is actually going to be an acidic salt, right? And the reason for that is that the ammonium ion, which comes from the weak ammonia, reacts again with water in order to form hydronium ions. Okay? So what does this mean for our titration? Okay. So, again, our titration must end at the equivalence point. So all of this has to be gone, right? So when all of that is gone, what's left is all of this, right? But when we've got this in the solution, that is acidic, right? So that means at the equivalence point, the solution is actually going to be acidic. Okay, and the solution is going to be acidic because the salt that is formed, right, is an acidic salt. Okay, so it's not acidic because there's still some HCl left or anything like that. The HCl and the ammonia has reacted, but the salt that is formed is actually acidic and thus decreases the pH of that solution. So in order for the equivalence point and the end point to actually coincide, to happen at the same time, we need an indicator that will change color in an acidic range. And that indicator is going to be our methyl orange. Okay, so that's why if we have a strong acid and a weak base, we have to use methyl orange. Okay? And then the last one for us to look at is to say, well, what's going to happen if we have a weak acid and a strong base? And I have a feeling that maybe you can predict at this point, but let's see. Okay, so for a weak acid, we might, for example, have ethanoic acid, right? Reacting with the strong base sodium hydroxide. So that would give us sodium ethanoate, like that, plus water. Okay, so for the sodium ethanoate, the ethanoate ion is going to be from the weak, and we know that that means that it's going to react again with water. And the sodium's not going to react again because it's from a strong substance. Okay, so what does it look like? Well, if the ethanoate ion reacts with the water, well, now what it wants to do is form its conjugate again, right? So it wants to form the CH3COOH, but in order to do that, it has to accept a proton from the water, which then forms an hydroxide ion. And the hydroxide ion is what makes something basic. Okay, so then this sodium ethanoate is going to be a basic salt. Okay, so basic salt means we put it in solution and it's going to increase the pH. Right, so at the equivalence point, when all of this has reacted, right, the solution is going to have this sodium ethanoate in it, right? And the sodium ethanoate, as we said, is basic, right? So at the equivalence point, the solution is basic, and so in order for the equivalence point and the end point to coincide, to happen at the same time, we need an indicator that will change color in a basic range. And that then is when we select the phenolphthalein. Okay, that's a fun one to spell and a fun one to pronounce. Okay, phenolphthalein. Okay, so you might notice that I've looked at strong and strong, weak and strong, strong and weak, but I haven't looked at weak and weak. Now, the reason that we don't really look at weak and weak is because weak acids and bases, when you titrate them against each other, actually gives you a very gradual change in the pH, which means that the color change doesn't happen quite as instantly, which means that the accuracy is going to be less for your titration. So basically, whenever you have a weak acid and you want to find its concentration, it'll be more accurate to titrate it against a strong base. So we don't really look at weak and weak because it's going to reduce our accuracy. Okay, so then we can just summarize here our choice of indicator and when we're going to use it. So we said bromothymol blue, strong acid, strong base, neutral salt. pH range of the color change is round about neutral. It goes from yellow in an acid to a nice green when it's round about neutral, and then after that it's going to go blue. Methyl orange, we use that for a strong acid and a weak base when we form an acidic salt. And so it's going to change color in a acidic pH range. And then our phenolphthalein, that is when we have a weak acid and a strong base, which then gives us a basic salt. And that's going to be colorless in an acidic solution, and then it's going to go a nice, beautiful pink in a basic range. Okay, so that's all I've got for you today as far as acids and bases are concerned. Thank you so much for joining me. I hope you've got a good amount of studying ahead of you. Remember that practice remains. Cheers.